we're just going to get, I'm not going to go into a lot of detail, but some real quick basics. Okay? First of all, any time varying signal, you can look at it, you can mathematically in a formula relate it in either the frequency domain or the time domain. The time domain is what you normally look at on an oscilloscope. And the two are interrelated. For a simple sine wave, the frequency is just the sine of the frequency, basically 2 pi f plus the phase shift. And the frequency of the omega, which is 2, frequency of omega is 2 pi f. Okay. So the two are interchangeable. Back in France, around 1800, a guy by the name of Jean-Baptiste Joseph Fourier figured out, worked with heat transfer, and had nothing to do with signals, just trying to figure out how heat, the way of converting time domain data into frequency domain data. And that's kind of come to roost here in a minute. And basically, he came up with Fourier transform, which is this little formula here. And then about, early late 60s, I guess it was, early 60s, two college professors figured out an algorithm for a computer that used digitized samples in the time domain, slices of data that were required, and how to convert that and determine the frequency domain data that represents that sample of data. And that's called a fast Fourier transform. And the neat one criteria is it only works as long as the samples have to be factors of 2. So 2, 4, 8, 16, 32, 10, 24, 24. Most people here have used fast Fourier transforms in their stuff. You have an ESP radio, it uses FFTs. You use FL-Digi. They're in the digital modes. They use FFTs. That's how they work. They get the data, they sample the frequencies, and put them in little bins in your computer. So let's talk a little bit about the time domain. Signals are in the time domain. You've got an oscilloscope. I think most people are familiar with that. You have the amplitude on the vertical axis, time on the horizontal axis. Normally you have volts per division or millivolts per division. So your sensitivity is not all, maybe good at 2 or 3 millivolts per division is about the best you're going to find. First oscilloscopes, they've been around a long time. First ones were galvanometers that rode a pen that rode on a rotating drum. They date back to the 1890s, over 100 years ago. First CRTs came out around the World War I era. By 1930, General Radio introduced the first general purpose oscilloscope. And up through the 80s, most oscilloscopes were the analog. Most guys are familiar with the Tektronix, 465s, whatever, 435s, 555s, 531s, whatever it goes. And the neat thing about the Tektronix is they came up and developed a sophisticated trigger circuit. Today, you can buy oscilloscopes, digital scopes, that will go up to gigahertz. Digital sampling, they have sampling rates 20, 30, 40 gigasamples per second. It costs some money, they're kind of expensive. It's interesting watching a 10 gigahertz signal in real time in the scope. As I said, that's what I just said there. So let's just say how we look a couple pictures. This is the general radio scope of 1930. This is CRT, box with a vertical lamp, box with the sweeper, okay, horizontal. A company called Dumont came out in the 40s with making oscilloscopes. The guy was kind of I think he loved general radio and in business. They also, remember Dumont Television, anybody? Dumont Television Network, Channel 5 here in DC originally, was Dumont. They built televisions, but they built a lot of oscilloscopes in the 40s and 50s. Tektronix came up with this idea that the Germans actually developed on how to trigger the sweep on a signal during World War II, and came out with the 511, the first commercial scope, which is how Tektronix really got into business way back in about 1948. Here's a 465. Looks familiar to some people? Should. This is kind of the height of the analog scopes. And today, we have digital scopes. This is the Tektronix unit there, which are about the same size as this guy. So, what's the scope do? Well, the basic analog scope, okay, let's cover the bottom first. We have a time base that sets up the timing, sawtooth generator, has a horizontal amp that drives the sweep across the horizontal plates, pulls the signal back and forth. You have an amplifier, drives a trigger that triggers the sawtooth generator, or then you have your vertical amp that drives the signal together. So that's our basic analog scope. I want you to understand this because when we get to the spectrum analyzer, I want you to see the difference. So frequency domain displays. You can think of an analog spectrum analyzer as a superheads receiver. It's got a swept local oscillator, and sometimes a linear or log detector with a display very similar to a scope, except that it has frequency on the x-axis and amplitude on the y-axis. A lot of modern systems have a peak-hold function. Let's do some of the digital scopes. You see the maximum and the real-time current waveform data. Most spectrum analyzers have what they call a zero-span mode, where that sweeping superhead receiver stops on one frequency, and then you start displaying the amplitude of the received signal that it's seeing versus time. So, we also have something called real-time spectrum analyzers. These are digital sampling systems that are FA transforms, which I talked about earlier. Basically, it transforms the power level received in various frequency bins across the display. Pretty much all of you have used real-time spectrum analyzers. It's what drives most of your digital software for all your digital modes. PSK, the FL Digi software, your software-defined radio, Sharp Plus, Camera Deluxe, whatever, all rely on basically our real-time spectrum analyzers. So normally this display of these guys gives you amplitude versus frequency like a conventional analyzer. You can get the waterfall display, right? I'm familiar with that. Coming down with all of the, and all that is just a cascaded list of all the FFTs. So as the FFT does the next one, does the next one, and it just flows down the screen. Most of them also can show samples of amplitude versus time data. So you can see the digitized version level of total amplitude I received at this for this sample as it goes on. So let's look at analog spectrum analyzer. Bottom, same thing as your oscilloscope, right? Time base, small tooth generator, horizontal amp. Big difference though on the vertical. You usually have a attenuator, sometimes a gig filter to a water filter, gig filter. You have a mixer. Then we have a swept voltage control oscillator, which is controlled by the sawtooth generator, IF amp, some filters, the log linear detector, video amp, and that drives the. So as you can see, the top part, the vertical amp is what's different from the scope. And a lot of the original scopes, like those that came from Tektronix, came as plugins to their oscilloscopes. And it's also true of Hewlett-Packard as well. So let's take a look at the analog spectrum analyzer. This beast is the first spectrum analyzer I ever saw and ever used. Back in about 1972, it was in the engineering lab at UVA. It occupied about a third of a 6-foot, 19-inch rack. But it was fun. I could look at this deviation of all the FM radio stations in town, between the 2 hours working for at the time, and actually be able to measure the, we could measure the deviation of the FM signals and see how wide they were, if we were overmodulating, whatever. So that's in early 1950s, I guess. This is a polar rabbit. I owned one of these 25 years ago and got rid of it when I got something a little bit better. We had one of these for sale from the estate auction this past summer, and nobody wanted it. I think finally Glenn was able to unload it and then
Cannibalized it.
and sold it, right? It was state of the art though, about 1960. And in the late 60s, Hewlett-Packard came out with the spectrum analyzer, and I acquired one of these. I still have it. doesn't quite work because it has a dead IF amp in it. It uses a unobtainium lighthouse tubes on the IF amplifiers. That was one of the first motor spectralizers that HP came out with, in two sections, an RF part, a display section. Okay, and then we have the 141, which is another HP unit. This has pull-out plug-ins. It has a time nation and an RF unit. There's like 4 or 5 different RF units covering different frequency ranges. There's a VLF, an HF, a UHF1, and then there's a microwave plug-in. We had 2 of these in the estate auction. Kevin, the 0PLH, bought one of them. I'm sure we got the other one. I have one at home that still works fine. I have 3 plugins for it. And that's when I got rid of the Polrad is when I got this guy, some over 20 years ago. This is a Tektronix 1A2. It was one of the first early digital scopes that had digital display, kind of neat function. It had the peak hole, it had a bunch of things. And this is a very heavily used workhorse scope during the 1980s. So this is an early 80s vintage. And then we have, this is an Agilent, or now Key Site, as they call themselves, 4407. They just discontinued these at the end of this year. I've used that one a lot. And that's kind of things are good. Like that particular one probably goes to 26 gigs. They have them available to 40 gigahertz. So, real-time spectrum analyzers real quick. Okay, we talk about these. Basically, here's what they look like. They're a basic computer. We have a mixer usually with a oscilloscope on steps, low-pass filter that drives an A to D converter. We have a sample clock, we have a signal conditioner, we do the FFT processing. It could be on board with high speed with a FPGA. It could be done in your computer like these software-defined radios work. And you have the display system, again, part of your computer, and then control interface. Key factors here, though, are, and price range is huge. Tuner frequency range, what range can you really cover? The sampling rate, and that helps determine the bandwidth you can look at, and the number of bits, along with processing speed for the FFTs, because you can only look at a certain amount of spectrum at a time. And if you want to look at more spectrum, you need higher sampling rates, you need higher speed processors, and the price goes up exponentially. So let's give us some examples of that. Okay, on the cheap side, you can do audio, like $0 free software for your PC, and you can do audio. For $12, you can buy one of the digital TV dongles. They have 8-bit processors, so they only have like 40 dB of dynamic range, which is one of the downfalls. They have 2 megahertz of instantaneous bandwidth, and of course the cost includes your PC and the free software for that. So that's kind of the low end. You really can get a real-time spectrum analyzer real cheap, but you don't have a whole lot of dynamic range. Let's go up a little notch. The thing on the center there is by Hound Dog, is the name of the company, and on the left of that is a unit that Tektronix just came out with to compete with them. These go for about a little bit under $3,000 for the Hound Dog, about $3,200 for the Tektronix. These are 14-bit sampling units. They do work through your PC. They have, the Hound Dog has about 24 megahertz of instantaneous bandwidth, so it looks at 24 megahertz shutter spectrum at a time. The Tektronix does about 40 megahertz over at a time. These cost about $3,000, and the tuner room goes up to about 6 gigahertz. So they're really popular. You want to do stuff like Wi-Fi and cellular, nice, cheap spectrum analyzer. 14 bits gives you, 86, 87 dB dynamic range, maybe up to 90 dB of dynamic range. Big difference. So let's go to the high end. These scans can cost up to $250,000. The one on the center there is one from Roding & Schwartz. The next one over to the right of that is a Agilent Keysight now. You can see a spectrum display. You can see a waterfall display over there on the right. These guys will do up to 20, 26, and maybe 40 gigahertz. They're 14-bit. They have between 110 and 110 megahertz of instantaneous sampling bandwidth. And of course, when you're looking at these signals, it's doing almost near real-time FFT. So if you're chunking 16 bits of data at a sampling rate of a couple hundred megahertz, it takes up quite a bit of processing power, which is why they're so expensive.
So do you know what kind of processor it uses?
I think most of these use an FPGA, so it's a hardware processing, the FFT, because you can't get, your computer processors aren't fast enough. So they're FPGAs. So controls and limitations, let's talk a little bit about. The major controls. One is the reference level in modern spectrometry. This is for your amplitude. So this is the maximum top display line. How many dBm is it? 0, minus 10, plus 20 that you set, and you have control for attenuation. Most spectrum analyzers have a burnout level about 1 watt input, so you don't put more than 1 watt into them, otherwise you'll fry the front end. Very important, your start and stop frequencies. So we're also, you can have a center frequency and span that does the same thing. Span being the width of the display, and tell where the middle is, and tell where to start and stop.
Complicated, right?
Resolution bandwidth. Basically, this is the bandwidth of your filters, and also your video bandwidth as well, that's setting, which is your low pass filter afterward. Resolution bandwidth is kind of important because it tells you basically how wide, how accurate your sample is in frequency. Obviously, you can't read, if I have a 5 megahertz resolution bandwidth, I can't read a frequency within 1 megahertz. You know? And then we have sweep time, which is set by the operator. Most of the spectrum analyzers let you display stuff, either have a log detector, so you look at the logs of dBm, or you can look at linears in a lot of cases as well, as linear detectors. Some of them also have RMS, so they read the RMS value. Zero span, when we mentioned earlier, it fixes the LO, so you look at your display is, what's the amplitude that, on that frequency I just tuned to versus time, so you actually get a look time domain picture. So problems of this, one problem limitation with conventional analyzers are that the resolution bandwidth, your sweep time and span are all interrelated. You know, because your sweep, these guys are sweeping by, right? So if your narrow filter is so narrow, it's sweeping by the signal so fast, it actually can't get an accurate reading. So you have to be careful. And things like the old 141 would have a little red light that comes on that says out of range. When that combination exceeds the limitations of the equipment. And some of the modern systems won't even let you do it. They'll just come back and say, complain that you have to change the setting. Oops. Back. Here. Okay, real-time analyzer. The problem with real-time analyzers are we have an A to D converter. And we gotta make sure we do not saturate that A to D converter with the signal. We have a real strong peak in there somewhere in time and saturate the A to D, then all your data is garbage. So one of the key things with the real-time analyzers, you should be very careful that you do not overdrive them and saturate your front end. Also, your resolution depends on the number of samples in the FFT, the sampling rate, and since you're based on the samples of data, digital sampling, you also can get some artifacts from the samplings, like spectral leakage, so you get some false signals in digital that really aren't there. Typically, the software has weighing functions, Blackline functions, a couple others that apply to your data set to try to minimize that. So accessories to have. So if you're getting a spectrum analyzer, what's the neat things to have with it? Number one is the tracking generator. This unit here has a built-in tracking generator. Like for the 141s, they were a separate unit you had to get. And what that is usually now a modern option. It usually goes up to 1.5 or 3 gigs. So it generates an RF signal at the same frequency as your spectrum analyzer is tuned to at an output jack. So it's sweet, it's putting out RF at the same time that the spectrum analyzer is looking at that frequency. So in essence, you can use it as we said down here in our bumper sticker, a scalar network analyzer. And we're going to be showing that in our demo. High impedance probe is another handy thing to have. Your normal input impedance of these guys is 50 ohms. Okay? If you want to try to use it to do some circuit troubleshooting and stuff, or looking at something other than 50 ohms, it's good to have a high impedance probe. You can buy one from HP for $3 grand. Or you actually build a simple one that basically provides a high Z input, 50 ohm output with a single op amp. Here's a
what's the advantage?
I thought we had another slide here. Okay, so we also have another thing is return loss bridge. Return loss bridge is nothing more than a Balun transformer, pair of precision 51 ohm resistors, 15 resistors. And basically, what that does with the tracking generator tied to it, you can measure the return loss and therefore basically get things like your DSWR versus frequency. So you can measure your antenna or any other component that you want and see what the reflection coefficient is for that. And another handy thing to have, which is right, this one, is a low noise amplifier. Could increase sensitivity. Most of your old spectrum analyzers basically drive a mixer input, and the things have a terrible noise figure, like 25, 30 dB. So putting an LNA in front of it can really give you a lot better sensitivity. Again, being careful you don't overdrive things, overload. So again, this is what it takes to build a high impedance probe. This is Steve Hackman's written a lot of QDX articles, and so just take one IC, we'll chip out capacitors, resistors, and you're good to go.
Is that the one you pay $3,000 for, or is that the one you pay?
This is one you build for works at 600 megahertz, and it costs you just probably about $20 to build one. So here we go. Think of a spectrum analyzer as basically it's a precision calibrated receiver. You can accurately measure input levels versus frequency. That's what it really does for you. I used one lately last year. We had a couple Boy Scouts who were building Yankee antennas and went to measure the gain and all. And the way we did that was I used my spectrum analyzer out there. So we had a calibrated receiver so we could actually tell the difference and measure the difference in gain for the different antennas as we looked it up to the SIG-Gen that had a standard source. We can measure FM deviation modulation characteristics. We're going to show you that. Probably all can't see it right now, but we'll get the camera up here. This has to be an FM broadcast station, and it goes to the top up here. So you can actually watch, as I did back in 1970 when I did my first thing with the spectrum analyzer, watch actually what the deviation of the FM transmitter really was.
Did the radio engineers at the station have anything like that so they could see?
No,
it
they just have a
before you saw it?
modulation monitor from HP or Gates Radio that, nothing like that. You can measure harmonic distortion easily with modulators and amplifiers with the spectrum analyzer. We'll kind of show you a little bit of that. We measure the harmonic levels of the transmitters, amplifiers, oscillators, whatever. We measure residual noise out of oscillators if we have good enough filters and a good low noise source of the mixer driving is one of these guys. And they're also great for troubleshooting RF equipment and tuning receivers and transmitters. Give you a quick example. I have an HG37, which is a phasing type exciter. I use my spectrum analyzer to adjust that the phasing modulator, right? So I got the absolute best possible unwanted sideband attenuation and carrier suppression. Because as I tweaked it, I could watch it in real time and see what that unwanted sideband is doing. So there, I couldn't do that with the scope. I couldn't do that with the BTVM. Spec Analyzer is great for that. With a tracking generator, you can do a lot. Basically, you can gain loss measurements versus frequency, which are really handy. You measure the loss through networks, cables, we're going to show you all that. Just basically any two-port device. We can use it to tune our filters, diplexers, LC filters, tweak crystal filters. We measure characteristics of crystals for designing filters. I've done that. So crystal filters, measured the characteristics of each crystal. 100 of them I bought on eBay with the Analyser. You measure gains and amplifiers versus frequencies, see what you got going. And then the return loss bridge, I said you did it earlier, and you got one port return loss visible versus frequency for any jack you're going to plug it into. So now we're going to do our demo here, and for this we're going to transition over here to the little mini cam so you guys can see what I do. So we're going to do some modulation measurements here. Key in HD with this old 1970 Tektronix 491. We're going to do some UHF signal, the HP generator here, and my RIGO, showing what happens with modulation, particularly if we overdrive the amplitude modulation. You can see what happens to the spectrum, which I think might be interesting. Then we're going to demo some insertion loss. We got 40 feet of RG58. Here Ron provided 10 feet of 174. And the infamous 40-meter filter from Field Day.
See what it really looks like.
So, anyway, so at this point I think we're going to go ahead and let this switch over here to the webcam. How are we doing time wise?
Doing fine.
The clock on the back of the room actually works, I don't care.
Okay, I think it got the camera.
Okay. Okay, we do. So let's get the, try to get her lined up real.
Where's the focus on this thing? A little further back and a little zoom in.
I want to get a little bit, well, this way a little bit so you know it's an angle. Let's turn on. Okay. So this is my vintage 491 Tektronix. And by the way, I have the book for it. Tektronix books on how to use it,
The owner's.
published in '69. And right in here is the picture of this spectrum analyzer. And the book is written around that. The moment, right now we're just looking at some FM broadcast stations. This is 50 kilohertz per division on a horizontal scale. So you can see, they're supposed to be modulating plus or minus 75, right? So it should be 1.5 divisions away from the center either way for their FM modulation.
Do they have point?
And they look like they're a little bit over actually, but some of that might be their SCA.
Is that the 3D viewpoint?
Yeah, well, the one problem with the, this is an analog, so there's no storage. You only have the persistence of the tube to look at what you had before. So that's kind of a limitation. So let's try, put that right in here for a second. And probably do not need the antenna. The LNA here. So I'm going to put the antenna directly in front of here. Because I just took all that gain out of there. This is the residual without the LNA. You see how weak the signal is comparatively to what it was before.
But it does, it looks pretty close to the same shape.
So what I'm going to do here,
Is that 10 dB per vertical division?
yes it is. So what I'm going to do here is, and this is KD40, is, tune this thing up here. A little wider so I can tune it in. One problem with oscilloscope is it has spurious signals.
I think that's what?
Spurious signals. So this is the HD here, okay? But this is fairly wide. This is 200 kilohertz per division, so it's 200 kilohertz with this. So I'm not really able to look at it
Why
right
is
now.
the signal intermittent?
I'm gonna do is narrow this thing down quite a bit. Get down to maybe 5 kilohertz per division. And then 2 kilohertz per division. Okay? And just jump frequency. This was not the stablest thing in the world.
The signal is pretty stable.
You see it's a little bit finicky. So here's my signal, and there's my FM DVH as I'm talking, as you can see here. Let's see that just a little bit better.
What's your baseline?
So right now, if I look at the FM, this is 2 kilohertz per division. So this is 10 kilohertz in the total width in theory here. And my resolution bandwidth is 1 kilohertz. So this is not the most accurate representation, but this is what we had back with the analog days of having the old analog type spectrum analyzer. So just give you an idea of what it looks like. And as you can see, I can actually measure the deviation of my signal as I'm talking to the HD. This is KD4 read. So let's switch over to something a little bit different. This is my rival spectrum analyzer. And I'm going to widen this up so I can tune this guy in a little bit better. So I set my span to 100 kilohertz wide. There's my signal. And we'll center the frequency a little bit. And then we'll reset the span back to
So what's the bandwidth of your rifle? No.
so right now, the display you're looking at, as you can see here, we have a 30 hertz, 300 hertz resolution bandwidth. That means that's the width of the signals that I'm catching the energy in bins for. And the span is 10 kilohertz. So each one of those division is 1 kilohertz across. And I'm going to apply some AM modulation to this signal. Okay? So I'm going to turn up the AM modulation. You notice the signal's coming up 1 kilohertz on either side of the carrier. So this is your traditional AM modulated carrier frequency, lower side band, upper side band, right? I'm going to keep cranking this thing up a little bit. And notice what happens when I start exceeding 100% modulation in the frequency domain. Can you imagine what that would sound like in the air?
Unfortunately, I heard it in communication stations in El Salvador.
You find that all the time before PSK stations.
Yeah. So this is what happens when you overmodulate. Your spectrum goes something like this, which is near about 100% modulation, to something that looks like that. And how broad is that? Well, let me go back and open my span up a little bit more. We'll do 50 kilohertz span here. And the problem is my resolution bandwidth just went to a kilohertz, and you don't see it quite as well.
So what's the screen bandwidth?
again, part of the deal here, as I mentioned earlier, is that resolution bandwidth is linked to my span in this instrument. So if I want to look really narrow, I have to do it over a very small part, or I have to do a manual override and decrease the sweep time. So that's kind of what an over-modulated AM signal looks like.
Wayne, you could have also done it with your older HP for Tektronix, correct?
Oh, yeah. Yeah, certainly. But this one's easier. So if I go to FM modulation.
You couldn't capture the percentage of your boss and say it's broken.
Let's read this real quick. Yeah. Little HP generator's drifting a little bit here. So I'm going to go to FM modulation now instead of AM. Again, we have a CW carrier, and I'm going to bring up playing FM. So this is kind of low-level FM. And I start bringing it up, you start seeing the FM sidebands. Now, there's one interesting thing about FM signals. There's a certain modulation index, which is the ratios of the deviation to the modulating frequency, where the carrier will go to 0. Right? You remember that from your extra class exam? Maybe? Let me show that to you right here. Watch the carrier frequency up there now, okay? So in the old days, that's how you calculated your deviation. You found the point where the carrier disappeared. And that, that told you what your modulation index was for the FM signal. Again, I can open that up a little bit. If I hit the right button. Okay, 20 kilohertz deviation. So
You're almost there.
you can see this is a pretty wide deviation here on this out of the sig jump. Okay?
So what is the ratio there?
So that's the, so now, our next set of demos real quick are going to be some insertion loss measurements. And let me put some adapters on here.
Right there.
This uses the, so this has a built-in tracking generator.
Can I explain one thing?
Sure.
Guys, a lot of you have the antennas on the back of your car, those cheap ones like I have, little quarter wave. Usually they come with RG-174. I've got the question many times, I'm running all 10 feet of that RG-174 through my car to my 2-meter radio. What's the loss? So this is exactly 10 feet of RG-174 with SMAs on each end. So he'll show you what loss is at 145 and at 440, because I'm using mine in my car for both. So we cut it exactly to that.
And probably 10 feet.
We'll see.
Okay.
That's 174.
I changed the resolution because I can do this on the nice digital one, so I got everyone here. This is 1 dB per division instead of 10 dB per division. And this is going from basically 9 kilohertz to 1.5 gigahertz in this display. So this is the insertion loss in dB. Down from the top is 0. The noise 20 dBm. The insertion loss on this particular cable versus frequency.
Not that bad.
It's not that bad. No.
So we can't see it at
So it's the
440. What can you give
Well, I
us?
can do it real quick.
Yeah.
We have another nice feature on the digital scopes called the marker.
Yep. On 145 and 440 if you can.
So, so if you focus in on that, a little better maybe.
Well, I'm not sure where the focus control is on this thing. I've got a zoom control, but,
Use the zoom, and see how that works.
well, that's,
It's just gonna make the blur bigger.
All right, that's and anyway, there's a marker there. The marker is, I don't know if you see me, he's right there where my finger is. But you can read out the marker level. It says it's minus 22. So it's
Oh,
got
that's
2 dB
four
loss.
forty-two, if I read that right?
So 2 dB loss at 440
2 dB at 440.
for 10 feet, guys.
Okay?
Just that 10-foot section.
Now, we have another cable that Ron made. This is 40 feet of RG58. Okay?
Is the loss of the nickel, if you have a straight line versus more or less?
Oh, my goodness.
Dramatic.
The question was, does the coil versus straight line matter?
No, not the transmission.
Not for some leakage.
Not for the insertion loss of the cable.
So, Lee,
Yeah.
why is the line here so jagged?
Step resonance.
Is that something to do with the
They are
materials?
probably due to resonances and grade.
Great resonance.
So what is that at 2 meters?
It's like hollering down a tube.
So you want 2 meters? Okay.
You get whistles and stuff like that.
Put my marker up.
You ever notice how that?
I understand that, that's an acoustic effect.
So the reference of this is 0 dBm?
Minus 20
Oh,
is my output.
So what's the loss?
The marker's right there.
So you're,
Is that 10
you're almost
or
10 dB loss.
Um,
Is that it?
All right, I'm just the antenna.
The marker's at 20.
Just on the cable.
I can't make it out either.
Can you read the number?
Looks like it says minus
Not minus
29 or something
21.
like that.
This was certain.
Which isn't equivalent.
It keeps looking like 29 to me on the screen.
No, it's 23, 22. It's about, okay, so it's 20,
what's the range on the screen?
it's about 22.8 there. So you got 2.8 dB of loss at 2 meters.
You're at 28 dB a loss?
2.8. Minus 20 is my reference, that's the level of signal putting in. Tracking zero output's minus 20. So it's minus 20 minus the 22.8, so it's 2.8 dB of loss at 2 meters with this cable right now. Okay?
And you're going from 6 to what?
This is 9 kilohertz to 1.5 gig is what you're looking at.
So Lee, you were gonna tell us, for those of us who don't have a regional spectrum analyzer, we have regional scopes, and we put it on the spectrum analyzer, FFT function. What is the difference?
The difference is, this is an actual sweeping oscillator, and this is conventional. It's really a hybrid in this one. It actually has digital processing on the back end, but the front end is sweeping like a conventional spectrum analyzer. The problem with the FFTs on the scopes that you have is what they do is they do a digital sample of the signal coming in from the wideband amplifier, right? The whole bandwidth of the scope, which is not very sensitive, because it has such a wide bandwidth, you have very low sensitivity, right? And it takes those digitized samples, it just runs an FFT on that data. So as you do a sweep across the scope, it saves that data, the amplitude versus time, the samples, and it just does an FFT on them. The problem is, you're looking at that whole, if you have a 100 meg scope, you're looking at a whole 100 megahertz. So your noise floor is way up here. So you really can't see very sensitive signals at all. This guy can see signals down to like minus 120 some dBm. You'd be lucky to see minus 50 with that scope.
That loss you attributed to the dielectric?
Huh?
That loss, is that due to the dielectric?
It's a combination of several things, actually. As I said, there's probably some grade resonance going on. You've got dielectric issues, you've got some conductor losses all in there. I think the reason it's so irregular is it's probably a lot of grade issues. Okay, so let's do another insertion loss of more just real quick.
That's because we don't look at the solid.
So can you take the scope?
This forgot to bring the UHF adapter. So I can't leave it this filter. Ron, where's that filter? I need to UHF to wait. I have here a helical resonator filter, which came out of an old GE two-way radio. And Rod just put some, this one for us.
So what do you have in there, Lee?
This is a helical resonator,
Helical resonator.
right, from an old GE radio. What I'm gonna try to do is tweak some of the tuning adjustments.
Oh,
Yeah.
Peaked at 149 max is what I had at.
Yeah. You notice that,
So is it sweeping now? Is your,
so I can tune this filter right now, watch the spectrum analyzer. So I can actually tune the stages on this filter.
And you're tuning it for,
I can change frequencies a little bit.
oh, you're tuning it for center frequency?
Yeah.
For symmetry?
So you can see right now it's at 149.
Perfectly good.
I'm not sure how far I can move this, but let's see where we're at
Well,
here.
the symmetry goes with
147, we're getting close to the 2 meter band.
So Lee, can you buy a good preamp and a good filter to put in front of the scope, front end of the scope, digital scope, and have a good spectrum analyzer? Can you
So
buy something like
I can actually tune this filter as you're seeing here. See how the shape has changed now?
Right.
So with the tracking generator, the scope, I can actually tune the filter easily. So if you're actually, trying to do this with a SIGGEN, I don't know, voltmeter or anything is next to impossible, right? And I can just watch it real time, what happens to my bandwidth as I tune the filter here. And that's,
You can also tell if you have parasitic effects.
so at least you get the idea of how this works here from what I just showed you.
were you only adjusting one parameter?
There's three capacitors in this filter. I was just tweaking the capacitors and the helical
So
resonator.
you were tweaking all three of them when you were doing that?
Just one at a time.
Okay,
Well,
Yeah,
all
you were
three
three,
did.
you know, three, you didn't just,
I didn't actually tweak the third one.
because if you just tune one of them, they get missile, you,
So I could probably do that. See, that's gonna go up, down.
otherwise you
They
get
can't
that
see that
distortion.
now, your elbow.
Yeah,
Right.
yeah, there you go.
It's hard. I should have longer cables on there.
Yep.
So anyway, I'll watch the display here and I'll tweak this. I get the screwdriver in the slot. So I can kind of move the frequency a little bit here. And I can also shape, as you see here, how it goes down and up. So I can kind of tweak it in there. And, that's around 147 right there at the center. So, okay, any questions?
Is your insertion loss there about 3 dB or what is it?
Yeah, this is about 10 dB per division, John, right now.
10 per dB.
Yeah, it's 10 per division right now. By the way, the Rigol is about $1,500 for the tracking generator in Japan, in China. There's a U.S. company called Hound Dog that sells a separate boxes. They have a tracking generator and SIGGEN, a spectrum analyzer that go to about 6 gigahertz that work through a PC. So they're like those little black boxes that you have to interface to your PC.
The ones you showed
And that's about, yeah. So they have just a plain spectrum analyzer, analog versus real time, and a tracking generator board, and it's about $1,600 for the pair. So you can, for less than most of the modern rigs today, actually buy a spectrum analyzer and tracking generator. So if you're really into homebrewing and building stuff, it's a great toy to have. Anybody else have any questions?
What's the minimum resolution bandwidth on the rifle?
The Rigol, I think it'll do down to 100 hertz.